Hi there and welcome back to Atomo Tutorials, and in this video we will be discussing something called the law of conservation of mass. It's something which is very relevant and is actually the reason why we balance chemical equations. So the law of conservation of mass states that no atoms are created or destroyed. And because of this, the same number and types of atoms occur on both sides of a chemical equation. This means that the mass stays the same throughout the reaction. Now, this is essentially a scientific way of saying that things cannot appear out of thin air and that things cannot vanish out of thin air. But if we look at the wording of this sentence, it says no atoms are created or destroyed. And then if we look at this chemical equation, if we were to cross out the 2's written next to silver nitrate and silver chloride, and then count the number of each atom on both sides of this equation, you will find that there are more atoms and different numbers of each atom on the right-hand side compared to the left-hand side. This, of course, means that the mass will be different. This means the mass has changed, and that, of course, breaks this law of conservation. So the reason we balance chemical equations is to ensure that the same number of each atom occurs on both sides of this equation. So we're going to apply this logic to something called a closed system. Now, what does this mean? Well, a closed system is a system or a space, I guess you could say, in which nothing can get in or out. And if nothing can get in or out, the mass within the closed system will remain the same, must remain the same. If we look at a conical flask, and if we're carrying out a precipitation reaction, this is where an insoluble solid is produced by mixing substances in a solution. If we carry out this reaction inside this conical flask, so if we assume the conical flask to be a closed system, we can have our silver nitrate inside the flask and mix it with some calcium chloride. In doing this, we will form our product on the right-hand side of the equation, one of which is a solid, a silver chloride, as indicated by the state symbol. So we've produced a solid here, but because we assume that nothing can escape or enter this flask, and because we know from the law of conservation that nothing can be created or destroyed inside it, the mass stays the same on the scales. And by the way, when I say assume, we assume this conical flask to be a closed system. I said that because in reality, if you did this in a school lab setting, you will probably have something escape from this system. It usually isn't completely 100% sealed. But definitely in theory, the mass would remain constant. So on a final note, before we move on to non-enclosed systems, you can also heat up or cool down a closed system and the mass will still remain the same. This next page looks at non-enclosed systems. Now, between the name and the diagram, you can probably figure out roughly what this means. It does mean that the system isn't closed, and so the flask in this case isn't sealed, and the contents of the flask are exposed to and are free to interact with whatever is outside. And so when a reaction takes place, the mass of the flask and its contents can change. The mass can either increase or decrease. If the mass increases, it will usually be because gas moves into the flask from the surroundings, reacts with something already inside the flask and forms part of the product. So the gas wasn't part of the initial mass to begin with, but as it reacts with whatever is inside, it becomes part of the product, which is most likely a liquid, a solid, or something dissolved. And it's therefore accounted for in the mass readings on the scales at the end of the reaction. A large part of the previous tutorial was looking at something just like this, where oxygen gas entered a vessel and reacted with what was inside, which was magnesium. And the mass increased because the oxygen from the surroundings formed part of the solid product. If the mass decreases, it's probably because one of the products is a gas and the reactants aren't gases. I'll explain what I mean by this. Let's say we have a reaction where we mix substances which are either solid, liquid, or aqueous, which means dissolved, something dissolved in solution. These are the reactants, and they make up the initial mass before any reaction happens. If one of the products is a gas, as the reaction happens, this gas product will be produced and it will leave the flask because there's nothing stopping it from leaving. It's a non-enclosed system. So something which was initially accounted for in the mass readings on the scales has become a gas through the reaction and has left the system. And so once this gas product has left the system, this means its mass is no longer accounted for and the overall mass of the system decreases. And so the example down here is a solid product, calcium carbonate, decomposing to form a gas. This carbon dioxide gas would escape the system and the mass would decrease. The only thing left which contributes to the mass after this reaction would be the solid product calcium oxide, which remains inside the system.